We're going to take one more partial derivative problem, but this time we're going to do an implicitly defined partial derivative. And so we're given the equation, hold on, book was a little far for me to read this off. The implicitly defined function x squared z plus yz cubed is equal to x. So this relates x, y, and z all together. And what we want to do is we want to find partial derivatives of z with respect to x and with respect to y. So this is somehow telling us how z is related to x and y, the same way x squared plus y squared equal to 2 squared tells you x and y are related to each other in a circle. And you should be familiar with implicit derivatives from Calc 1. You would have done it for functions like this, but you might not remember it. That's okay. It's been a while. We're just going to do an example with multivariable functions so that you can see it again. So the approach is just going to be to sort of pass a derivative all the way through both sides of our equation. Oops, 2. And this is why I like this notation with the d's instead of the f sub whatever notation, because it's easier to see how to do this. So if I want to know a derivative with respect to x, I'm just going to take a derivative with respect to x of the thing I was given, x squared z plus yz cubed. And if I take the derivative on the other side, it should stay equal. So I'm going to start on this side because it's way easier. The partial derivative with respect to x of x is just going to be 1. Derivative of x with respect to x is 1. Even though we introduced this weird notation, nothing really special has happened. And then I'm going to take a partial derivative with respect to x of this. So I know that derivatives can be applied to both parts of a sum separately like that. You know, the derivative of x squared plus x is the derivative of x squared plus the derivative of x. That's something I promise you know. And then, let's see, d dx of yz cubed. That part's going to be a little easier for me than this part. So I'm going to go ahead and say, okay, this is basically the same as 7z cubed to me when I'm thinking about x, because y is basically a number. So y could kind of come outside that derivative. And then I'm just taking the derivative with respect to x of z cubed. Now this is the part where it gets a little bit tricky. Z depends on x, so I'm going to have to use a chain rule here. You know your d dx of f of g of x tells you it has to be g prime of x, f prime of g, like that. So here my quote f is z, and then in the inside is x. So I'm going to need to do, this would become 3 times z squared, where z is my g, and then I need to do the derivative of that quote g. So then I'll have dz dx. So I may have misspoken earlier. My z is basically my g, and my f is basically something cubed, for that comparison right there. And then when I'm taking my partial derivative with respect to x of this first term out front, now I have an x squared and a z. So everything inside this parentheses depends on x. This is going to be a product rule for me, x squared times z. So I'm going to say, okay, the derivative of x squared with respect to x is going to be 2x times z unchanged. And then I'm going to keep my x squared unchanged, and I'm going to have to look at the derivative of z with respect to x. And so what I used right there was my product rule, fg prime plus gf prime. So, you know, my g was z and my f was x squared. Oops, 2xz plus x squared dz dx. All of this on one line. Now I'm trying to solve for dz dx. So here's dz dx, here's dz dx. I'm going to solve for it. I'll just pull it out front of everything. It's times x squared plus y3z squared, and it's equal to 1 minus 2xz. So dz dx is 1 minus 2xz all over x squared plus y3z squared. And you could rewrite that in any order that is less confusing to you. Maybe you'll put the 3 out front of everything else, because that is the way that you usually like to see functions. So I'll do that at least for you. There. Okay, so let's go ahead and do the exact same thing. I'll be a little bit quicker this time for dz dy, just so that you have more practice with it. So my x squared z plus yz cubed equal to x, and I'm looking for dz dy. And maybe you could go ahead and just try this one on your own to check if you understand it. Pause here, skip to the end of this video, and check your answer. But I'm going to talk through it in case it was a little sketchy the first time. I want to know a derivative with respect to y, so I'm going to apply a derivative with respect to y to both sides. This one's actually going to be a little bit easier on us than the last one. So the right side is still simpler than the left side, so I'll start there. Derivative of x with respect to y is 0 because x may as well be a number as far as y is concerned. On the left side, I'm going to pull my two terms in parentheses apart. Again, showing this much work is not necessary when you're taking derivatives. I'm just doing it to be really deliberate and slow while this is new to us. Derivative with respect to y of x squared z is just x squared, and then the derivative with respect to y of what's left inside, z. And the reason for that is because I can pull x squared outside of this derivative because x is a number as far as y is concerned. This dy of yz cubed is going to need to use a product rule because I've got y times z cubed, and a chain rule because I've got that z cubed. So let's go ahead and see what happens. I take the derivative with respect to y of y, that's 1, keep z the same, so I've got my z cubed there. And then I'm going to have, keeping y the same, and I'm going to look at the derivative with respect to y of z cubed. Let's do that last derivative on the final line. So derivative with respect to y of z cubed, we just use our chain rule. It's 3 times z squared times dz dy. And now I just want to solve for dz dy. So I've got that it's multiplied by x squared and y3. I'll just go ahead and fix that right now. 3yz squared. That came from here and here. Equal to minus c cubed. So my dz dy is minus c cubed. That's a bad underline. All over x squared plus 3yz squared. And that's just going to be how you take derivatives of implicitly defined functions. Should be really similar to stuff that you knew how to do in another class, but it may be kind of